We're continuing with section 2.8, estimating zeros by bisection. So existence of zeros, if f is continuous on enclosed interval a and b, and if f of a and f of b are non-zero and have opposite signs, then f has a zero in the open interval a and b. And so this is a direct consequence of intermediate value theorem. When you set m equal to 0 and basically you set f of a and f of b to have different opposite signs and set m equal to 0. So let's see. What we do with bisection is we find smaller and smaller interval by bisecting an original interval where f of a and f of b are of different signs, are opposite signs, and we bisecting it, and by bisecting it and finding a smaller and smaller interval, that this is true, that the endpoints are basically and smaller, and the endpoints give you the opposite sign f value basically. Bisecting means cutting in half. So let's say this is the picture. We start with interval a and b, which a is 4 and b is 10, and then we realize that over here the f of a is positive, f of b is negative, and so this is an interval that contains a 0 according to this theorem, according to an intermediate value theorem. And so we bisect it. How do we bisect it? 10 plus 4 divided by 2 gives you the midpoint, and then you check the midpoint. And the midpoint, either f value is positive or negative. Then you decide to pair up the midpoint with either 4 or 10. As long as the f of 4 or f of 10 are the opposite sign than f of 7. So here's the f of 7. I realize that f of 7, look, when you look at the f of 7, it's above the x-axis, therefore it's a positive value. So I paired it up with 10. And at this point, so we have a smaller interval. Now our new AB interval is 7 and 10. Find the midpoint, because you're bisecting. 7 plus 10 divided by 2 is 17/2, which is 8.5. Now 8.5, find the y value. In this case, I know y value is going to sit below the x-axis. So y value is going to be a negative value. So I replace the 10 that had a negative value with 8.5. Now, the interval 7 and 8.5, f is different sign on that one. Now you bisect it again and again, and find pair up the midpoint with one of the endpoints that is opposite sign, and do that repeatedly, and you see that the interval gets smaller and smaller. And so right now in this interval between 7.75 and 8.125 we have a 0. So with the error, let's say 25 and 1.27, the error in finding the 0 of the function is 0.25 plus 120 plus 0.125, which is 375. 0.375 error. I can find the 0 of the function basically. So that's the and that's how we. So the interval has to be smaller than the error if we are finding within a certain error. Now let's try to do an example. Example 1, show that f of x equal to cosine squared x minus 2 sine of x fourth has a 0 in 0 and 2, then locate the 0 more accurately using bisection. It doesn't tell you what to use for the error, so you can find a good error and choose. Usually in the homework assignments or exam assignments, they tell you the error. So first, to show that there is a 0 in interval, open interval 0 and 2 of this function, you evaluate the function at 0. So f of 0 is cosine squared 0 minus 2 sine of 0, which is 1, is a positive value. Then find the f of 2. F of 2 is cosine squared 2 minus 2 sine squared 1/2, and if you plug that in, and these are in radian, if you plug that into your calculator, you get negative 0.8 is a negative value. And so according to intermediate value theorem, f has a 0 on the interval 0 and 2. Now let's use the bisection to make a more accurate 0, because interval 0 and 2 could be it's a big interval. We want more accurately we want to find a more accurate value. So what you do is you take the interval 0 and 2, you find a midpoint. By the way, the tables are important, otherwise it will be all over the place. You cannot find the values that you found, and it will become very difficult. So function value at 0 is equal to positive, is a positive number. That's what we figured out. F of 0 is 1. At 2, it's a negative value, and that's what we figured out. F of 2 is negative 0.8 almost, and approximately. And then so we have to find a midpoint. Midpoint between 0 and 2 is 1. Find f of 1. It turns out to be approximately negative 0.2. And so what we do is we replace 1 by 2 over here, because we would just replace the one that would give the function would be negative at by the new value that the function would be negative at. And so 0 is between 0 and 1. And so this way, so the next step is again, remember, at 0 function is a positive value, at 1 it's a negative value. Find the midpoint between 0 and 1, average amount 0 plus 1 divided by 2. F at 0.5, if you plug it into here, in here and in here, plug 0.5 in for x in here and here, then you get f of 0.5 is approximately 0.5. So now 0.5 is a positive value, so that's the f value is a positive value. Replace 0.5, replace 0 by 0.5, because 0 was giving a positive f, and 0.5 is giving a positive f. Now you have a 0 in 0.5 and 1. So and then continue doing this, and every time you find a midpoint, you find what the sign of the midpoint is, and then you replace replace one of the endpoints by the midpoint. The endpoints that has the same sign as the midpoint. And it gets smaller and smaller. And then we stop right here, because I see that basically I figured out one decimal place accuracy for the 0. See, the interval starts with 0.8125, and then the other endpoint is 0.8125. 0.875. So the 0 has to be at 0.8 something. Because both sides of the interval have the 0.8. And so we have 1 decimal accuracy in here. So we use intermediate value theorem a lot when we were trying to approximate that the graph of a function is crossing x-axis or not. Let's say, does cosine of x equal to x have a solution? First thing is, again, I'm trying to set one function to another function. As soon as the two function comes in, using intermediate value theorem is just basically we need one function for intermediate value theorem, and therefore you want to subtract the two of them, and you're interested in an equality. The equality is where the difference of the two function is equal to 0. So that's the part that we use very often with intermediate theorem, intermediate value theorem, to compare the value of two functions rather than one function. So you find the difference of them, and then when the difference is 0 is where the two of them are the same. And so interestingly, the difference function f is at 0 is a negative value, and f of pi half is a positive value. So there is a c between f of 0 and f of pi half, that basically f of c is going to be equal to 0. What is f of c? It's c minus cosine c equal to 0. So c is the root, is the value that makes the two function equal, and so it's the solution to cosine of x equal to x, and it's between 0 and pi half. The next is show that square root of 2 exists. So sometimes and for example, this one in the previous one, I can algebraically solve for c and find c, but I can find a polynomial whose roots is a square root of 2, basically, and so that's part of the sometimes you just use intermediate value theorem, and sometimes you basically know how to solve for the equation and find the actual root. And so now, what is the polynomial whose root is square root of 2? That would be x squared minus 2, right? And so we can apply the intermediate value theorem to x squared minus 2, and x squared minus 2 is basically, if you plug in 1, you get 0. If you plug in 2, you get 2, and so if you plug in 1, I'm sorry, you get -1, and if you plug in 2, you get 2, and therefore there should be a 0 between 1 and 2 for the polynomial. And let's call that c value, and it's c squared minus 2 equal to 0, and so c squared equal to 2 exists, and that's square root of 2 exists. By the way, if you notice that here we draw both graphs, and that graph basically crosses the x-axis only once. This graph crosses x-axis twice, one at square root of 2, one at x equal to negative square root of 2. Now, how about f of x equal to x to the 4th plus x minus 4? Finding the so interestingly enough, some of these finding the value of the root is not algebraically possible, and so just knowing the root exists or using bisection to find the root is important for us. And so in this case, we find that f of x is changing sign on interval -2 and -1, and also at 1 and 2. And so it has to have 2 zeros basically. And then the other part is that, is this the only, how do we know that they are the only zeros? We either have to find other intervals that actually include zeros, and that requires a lot of looking for the intervals, and we may not be quite successful, but knowing approximately what the shape of the graph is helps us to find whether or not we have 2 or more zeros.